Hello, in this short video we're going to take a look at the definition of separable differential equation and solve one such equation. A differential equation is any equation that involves a derivative. So a simple example is dy dx equals 2y. You can see the derivative of y with respect to x involved there. In Math 266, 267, you'll study second order differential equations. An example is d squared s dt squared plus 4s ds dt plus t squared s equals 5. In this case, you have a second derivative as well as a first derivative of the equation. In each equation, the idea is to find a function, in the first case y, in the second case s, a function whose derivative, derivatives, when you calculate them, satisfy the equation. We're going to study separable differential equations. An equation is called separable if it is of first order, that is, the highest derivative that appears in the equation is a first derivative, and this derivative can be expressed, usually on the right-hand side of the equation, as a product of two functions, each a function of one simple variable. So separable equations will typically look like this. In this case, we'd be looking for y is a function of x, whose derivative happens to be whatever the function capital F is times the function capital G. This equation is separable if you can separate this into a product of two things, one function of f, one function of g. The variable names will change, often depending with the application. So if we're looking for z as a function of s in this differential equation, we would have dz ds, z is a function of s, and in our initial equation we'd express that as a function of h times a function of s. Not every differential equation is separable. Here's one that is not, and that's because there's no way you can factor this expression 2y plus x into something involving y times something involving an x. Okay. So the plus here kind of messes things up. If this had been 2x times y, then it would have been a separable equation. So we studied these equations, differential equations, because they're important in describing processes in science and engineering. And we only do this because often it's easier to describe the rate of change of a process, how something's changing, than it is to describe the phenomena directly. So these equations are generally easier to solve than perhaps it might be to derive the equation directly. The separable equations are extremely easy. We're going to solve those by the following scheme, simply putting all the variables containing, or all the expressions containing one of the variables on one side of the equation, and all terms involving the other variable on the other side, and then integrating both sides. So we'll take a look at one example of this. Let's solve the initial value problem. dr dt equals 2 times the quantity r squared plus 1 divided by t squared with the condition r of 1 equals 0. So a differential equation like this is called an initial value problem if it has a side condition such as the r of 1 equals 0 that tells us the value of the solution, r in this case will be a function of t. This tells us what the solution must be equal to when t equals 1. We'll see that this helps us determine the constant of integration when we do the integration used in solving the problem. By the way, this is a separable equation. Pretty easy to see that here, but you can separate this more formally as r squared plus 1. There's a function involving only r, and then times 2 over t squared. So a function of r times a function of t. Of course, the 2 could have gone anywhere. I could have moved the 2 out in front here and let the 2 kind of go with the r squared plus 1 portion also. So when you have a separable equation and want to solve it, the first step is to separate the variables. So here we have put the r expression, the 1 plus r squared on the left. I do that by dividing both sides by r squared plus 1. And I've just left the 2 over t squared over here on the right. We'll take care of the dr dt in just a moment. Now, formally, our next step is multiply both sides by dt. This introduces a dt on both the left and the right, as you see. And then in the process, we use the definition of the differential. Back in chapter 4, we studied differentials, and they were defined as follows. The differential of r dr is given by dr times r prime of t dt. And of course, r prime is dr dt. So we have dr is dr dt over dt. We're going to take this expression dr dt times dt that we see here, replace it by dr, and this gives us our separated form. Now, normally when you solve these equations, we're just going to jump from the equation right to this point. And I often think of doing that as just I multiply both sides of this expression by dt. And if I treat dr dt as a fraction, the dt's cancel, leaves me with dr on the left, and introduces the dt on the right. But here's the separable process. So in the end, all the r's on one side, there are no t's on the left, and all the t's on the other side, there are no r's there. Once you have things separated, we simply integrate both sides. So throw an integral sign on each side as we did there. And notice for ease in integration, we've written 2 over t squared as 2t to the minus 2. So we have, of course, added differentiation. Integration can be a challenging problem in some circumstances. In this case, it's not too bad because we have 2 recognizable antiderivatives. We know that 1 over 1 plus r squared is the result when we differentiate inverse tangent of r. So the integral, or indefinite integral, or antiderivative of 1 over 1 plus r squared dr is inverse tangent of r. Likewise, 2 over t to the minus 2 is easy to integrate. We get 2t to the minus 1, so add 1 to the exponent, divide by the new exponent, and that gives us minus 2 over t plus c. Now, technically, when we do an antiderivative, we should add a plus c to both sides, a plus c over here after differentiating, and a plus c here. But since we could then subtract the constant from, say, the left and combine it with the constant on the right, we generally just introduce one constant, in this case on the right side of the equation, the plus c. So this accounts for the constants of integration in both of these integrals. We can now determine the c because we have an initial condition. If we did not have an initial condition, our solution would involve this constant plus c, and we'd be getting a whole family of solutions. But the condition r of 1 equals 0 tells us that when t equals 1, r is 0. We can use this to find the value of t. So we're going to take our equation, this is just transcribed from the previous slide, and put in r equals 0, t equals 1, and it gives us the expression right here. Since inverse tangent of 0 is 0, we conclude that c has value 2. So all we have left to do is just state our solution. Our solution is given by inverse tangent of r equals minus 2 over t plus 2. Now, this is an implicit solution. Implicit because we don't have r separated as a function of t. And when you solve differential equations, that often happens. Expressions on both sides are so complicated, it's hard to isolate, say, the dependent variable r in this case. So solutions of this form are perfectly okay. Of course, in this case, we know a bit more about the inverse tangent, and this expression is not too complicated. If we take tangent of both sides and use the fact that tangent, inverse tangent are inverse functions, we can actually get an expression that shows r as a function of t. So up here, we've just taken the tangent of both sides, tangent of inverse tangent here, and tangent of minus 2 over t plus 2 on the right. And this tangent of inverse tangent of r gives us the r back. So either one of these, the implicit or the explicit, are perfectly good solutions. Finally, you can check your solutions to these kind of equations. Remember that this expression r we found is supposed to satisfy this differential equation we started with. So if we just differentiate our answer, we should be able to show that the derivative of this answer can be put into this form. So let's actually go through and do that derivative. And so here it is all at once. So again, I'm differentiating this expression. So here's dr dt. When I differentiate tangent, I get secant squared of minus 2 over t plus 2, and then by the chain rule times the derivative of what's inside there. And so when I differentiate this part, I get the 2 over t squared. Now, this doesn't really look much like our differential equation, but as is often the case, if we know enough identities or are willing to do some algebra, we can make this work. Here we use the identity that secant squared is tangent squared plus 1. So secant squared of minus 2 over t plus 2 is the tangent squared of minus 2 over t plus 2, and then plus 1. Now, finally, remember tangent of minus 2 over t plus 2 is r, and so we're seeing r come out here finally. And so the tangent squared of minus 2 over t plus 2 is the same as r squared. So our derivative dr dt looks like r squared plus 1 times 2 over t squared, or with a little algebra, 2r squared plus 1 over t squared. And so that verifies that our solution does satisfy that differential equation. The other part, of course, would be to plug in t equals 1. So we want to make sure the initial condition r of 1 equals 0 is satisfied. And it's easy to see if you plug in t equals 1 here, you do get r equals 0. So because the derivative works out right, and this r satisfies the initial condition, this r is a solution. In fact, it's the only solution to the differential equation. So this is not a hard process. The two things you want to take away here: how do you recognize a separable differential equation? And that's that factoring business. Can you factor the expression equal to the derivative into two functions, each involving one variable? Then it's just a matter of putting the variables, all of one variable on one side, all of the other on the other, and then doing the integrations. So just this, as everything, takes some practice, so have some fun with this. Good night.